Now we can look at a consequence of conservation of momentum and the center of mass and what we know about systems of particles. So we're going to look at a system with two objects. The first object is me, and I'm holding a wrench. And the wrench is the second object. Okay, so imagine me and the wrench are floating out in space, and I decide to throw it. So by now we know that in doing so, I've given some of my momentum to the wrench. So the wrench is going to be moving to the right. Well, initially the center of mass was located, probably just slightly further from me, because almost all of the mass in the system is in me. So wherever my center of mass is, it's just going to be slightly shifted toward the wrench. After I throw it, even though the wrench is much less than me, if we look at our formula for the center of mass, which is my mass times my position plus the wrench's mass times the wrench's position all over our total mass, which is almost all my mass. But that doesn't matter, because as the wrench gets further and further away from me, its distance increases. So while my mass stays the same and this distance increases, it would seem like this means that the center of mass is also going to move. It's going to follow the wrench. But we know that can't happen, right? Because the momentum of the center of mass initially was zero. Both the wrench and I were at rest, which means even at a later time, the momentum is still zero. The only way for that to happen is for the center of mass to not move, but instead for me to move to the left. Because now, if my position becomes negative in such a way that it cancels out everything that's being added to the new position from the wrench moving, then that's going to allow the center of mass to stay in the same place. So by me throwing the wrench, not only did I push the wrench to the right, I actually pushed myself to the left. So let's look at an even more complicated example. Let's say now I'm on a spaceship, and we're going to let this spaceship be the system. And inside this spaceship, also included in the system, is me and a baseball. Now the baseball I was originally holding, but then I decided to let it go. And because I'm in space, there's no gravity. So the baseball is just floating in air. Of course, the spaceship's moving at a velocity v. I'm inside, moving at the same velocity v. And because the baseball never has any forces on it, even though I let go of it, it's still going to be moving at the same velocity it was when I was still holding it, when it was still moving, when we can treat the spaceship, me and the ball, like a rigid object. So I've let go of it. There have been no forces acting on it. Its momentum and its velocity haven't changed. But I thought this is kind of cool, because I was holding this baseball. Here I am in space, I let go of it, and it's just floating there in front of me. So what I didn't notice is in front of me was a giant wall. So moments later, I crash into the wall. In other words, the velocity of the spaceship becomes zero. Since I'm attached to the spaceship, my velocity becomes zero. The baseball crashes through the window, and it's going to continue moving at its same velocity until it too eventually is going to hit the wall. So now we've all stopped. Well, what does this say for the system's momentum? We said that if we look at the entire system, that its total momentum doesn't change. So even after interactions, the overall momentum should be the same. So what's going on here? Well, what we neglected to see and think about is that this wall, we can't use this as our system without including the fact that we have this wall that's attached to the earth. So if we're giving up all of our momentum, we must be giving it to the wall, which means in some sense the wall must move. But we know the wall's fixed. The wall's fixed to the earth. So not only does it mean that the wall has to be moving, because it's attached to the earth, it means we're actually giving our momentum to the earth. So we're moving the wall and we're moving the earth. Now that might seem counterintuitive. I mean, you can just imagine if you throw a baseball at the wall and it hits the wall. Well, the wall's connected to the earth, so it would seem like every time if you throw a baseball against the wall, you're actually giving your momentum to the earth and you're moving the earth. And the truth is, you're right. That's exactly what happens. The difference is the mass of the earth is so much larger than your mass or the mass of the baseball that, remember, momentum is mass times velocity. So even though the momentum that I have, I may be throwing the baseball very fast. The mass of the earth is so large that in order to compensate, it just has to shift its velocity by just the tiniest bit. But think about this. This means if you're in a room and you're breathing and you have air particles, coming out of your lungs toward a wall, that those air particles are actually going to affect the wall. And it's true, and they measure this, and it's actually in picometers. So we're not talking about a very large amount. We're talking about like 10 to the 14 meters, 10 to the minus 14 meters. But it's a real measurable effect. So in the next video, we're going to talk about what an inertial reference frame is and why our thinking in this case was wrong and why we needed to make sure that we included the Earth.